So this is my Lab 3 circuits. The purpose of this lab is to use multimeters and calculations of conservation of energy and charge to learn about the behavior of resistors and capacitors in circuits. We use Kirchhoff's loop rule and conjunction rule and Ohm's law for calculations. And then by the end of the lab, we determined that there was a current of about 0.0192 amperes going through the series circuit and 0.056 amperes going through the circuit in parallel. So these are the equations for Kirchhoff's loop rule and junction rule. And then Ohm's law derivations for a battery, resistor, and capacitor. And then in the experiment, we set up multiple different circuits and measured values of current, potential difference, and the amount of time it took to charge and discharge a capacitor. The assumptions are that each battery is 1.5 volts, making the total electromotive force of the system 3 volts. And all connections within the circuit are sound, and energy and charge are conserved. The system is the circuit itself, and the surroundings are everything but the circuit. Initial conditions are that before any of the circuits are closed, there's no current flowing through them, and then capacitors initially have 0 charge. So it's part 1 of this experiment where we did the series circuit. We found the current flowing to be 0.0192 amperes, and then when we replaced one of the ammeters with a voltmeter, we saw that the change in potential was 0 volts, which makes sense because it was just like going through a wire, which is a conductor, so. And then we measured the potential difference across the 47 ohm resistor, the 100 ohm resistor, and the batteries. And across the 47 ohm resistor, it was 0.909 volts, negative. And then over the 100 ohm, negative 1.948 volts. And then over the batteries was 2.9 volts. And then we put the circuit in parallel with the ammeter, another ammeter, and then the current changed to 0.052 amperes, and then the bottom ammeter showed 0.0506 amperes. Yeah. This was our graph of potential decreasing throughout the circuit, and that shows that the conservation of energy throughout the circuit. So this is the data that we calculated. Our experimental data showed that the 47 ohm resistor had a resistance of 47.34375 ohms. The 100 ohm resistor had 101.45833 ohms. And then the wires and ammeters had a potential difference of 0, so they had no resistance. Okay, and then we made an RC circuit with a 20 ohm light bulb, and this took about a minute for it to charge and discharge, and then with a 10 ohm light bulb was like 15 seconds. So there was some error in this lab. The discrepancy could be because our multimeters could have had slightly incorrect readings, and then the resistors could be old and possibly have changed resistance with age. So what if we charged a capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? So with no resistor in the circuit, the capacitor would charge instantaneously, but this wouldn't happen in real life because batteries have a resistance and the wires also have a non-negligible resistance. So in conclusion, we learned how to build circuits and measure the current and potential difference through multiple components of a circuit using multimeters. We confirmed Kirchhoff's laws of conservation of energy and current within circuits. And then we were able to find experimental values of resistance to be very close to the true values of resistance. Thanks.